also technical talk, but I will try to put some justification why we're doing certain things. Please feel free to ask questions. And they will come through the Q&A or chat, and then probably Hin will just pick it up and then unmute you, or he will ask your question on behalf of you. Okay, so then it's a group work. It's not only my work. I put names of Adriana and Ross, which contributed to the hands-on session, which is like a key element. And then my lecture is only addition to hands-on session. Okay, so today I will be talking about MoFEM a little bit, multi-field formulation for plasticity, why we're doing that, H-diff contact formulation, and mixed formulation for large strains applied to incompressible hyperelasticity. Okay, so then both problems, both codes, which were formulations which I will present to you, are made to be applied in the industry. There is some industrial application behind of it, but when we do the things, we making a toy and 5 problems. But those problems, both multi-field plasticity and mixed formulation for large strains, involve both a contact and then physical nonlinearities, different kind of physical nonlinearities. What is the common element of those problems is that we're dealing with the unilateral constraints in both of case of the plasticity or the contact, which is a tricky thing to do, as you may know. So later on, what you will find out with Adriana and Ross, that we'll have 2 notebooks to walk over them. One will be showing a necking problem solved with the multi-field plasticity. There will be as well those notebooks which will have a theory, the equations in them. In second problem, we'll look at the hyperelasticity, but we'll show how you can calculate a posteriori error estimator for nonlinear problems with the large deformations, which can be a tricky thing very often. Okay, so MoFEM is developed by a group mostly in Glasgow. You can see most of this my colleagues which develop on that picture. I don't know, this is probably 10 years so from the past, but we're doing that every year. This is from pandemic. I don't have a picture from this year. And then I want to say that the Glasgow is a nice place to be, because we can go to mountains or we can go to sea almost in 20 minutes, 30 minutes, if we like to. You are welcome to join us. Even we are not only restricted our contributors to Glasgow. Okay, and then software. So then software engineering and development of code is a social thing more than technical. And then you can see how it works over the years. Then you can see many people working. This is a group work. So there is not true leader, in fact, because everybody working together. And then we see software as a kind of the garden where we cut branches, we grow new one, we plant the new plants, and so on, to solve the more and more complex problems. So just that to make you aware, we're working with the Jupyter notebooks. So Python is only an outer interface through which you run the code, but everything which we run is in C++. And then we focus now on solid mechanics, but in principle, the code which we develop has many applications, which include the fluid mixture of fluids, problems with the surface tension, shallow waves on manifolds, FSI, fluid structure interaction, bone remodeling, and then those classical structure integrity problems like plasticity. But we can do as well not typical things like solve light intensity equations in order to recover a 3D image of the liver cell from the microscope, and then we're solving PDEs, and as the result of that, beautiful images like this one in the corner emerge. What I want to say that MoFEM is a tool for solving PDEs in the applied problems, engineering problems. And then, but here we focus mostly on solid mechanics and mixed elements. This is like fraction of our activity. So, but MoFEM is not built from scratch. It has many tools developed in the different places around the world. And then, for example, PETC and MOAB, and those tools are developed in US in Aragon laboratory. They are great tools which constitutes like a skeleton of the MoFEM, and MoFEM is building on top of them. But there are many other tools like ADOLC for automatic differentiation, F-tensor for tensorial operations. We have to handle several data formats, interface with the different pre and post processors or low level measures. We integrate the code with the tools like mFront, which allow us to add the large set of the constitutive models. This is developed in SIA in France, and then but the MoFEM overall is built on the MIT license. So what that means that what we do in Glasgow, we try to do it as open as it possible. But if industry want to take over certain parts of our code and apply in their design or work, they can do that because they can take open code and then they can develop it a little bit further at the things which they don't want to expose to the outer world, and then use it internally. Okay, and then another thing which is important, we can wrap all this ecosystem into the Docker image. And this is what will happen, that at the end of this, when cars will finish, the workshop will finish, we'll make a Docker image that you will be able to deploy it on your laptops or local servers with all the tools, all the notebooks which we presented over here. So the cloud which is run at the moment will be running only for a while, but at some point we'll shut it down, and then but you will have the Docker container which you can run it locally. So then when I'm talking about MoFEM, I'm talking about the complex software which is designed to solve complex engineering problems. So we have to handle, I can see at the end, the complex geometries with the contact, with the complex material properties, with the complex phenomena like fracture, okay? So I presenting to you, I will show to you all the tools like mixed elements, but those mixed elements at the end can be deployed on the problems like this one, for example, ultimately, okay? So this is the paper. If you are, I will not talk about this problem, this particular problem, but if you are interested, we published this paper recently that you can look at it, how these problems like that are calculated. One important thing as well, we're looking for a postdoc So if you want to work with us, please apply. This work will be related to the structural integrity of the nuclear reactors, and it will be you will be working with the EDF. This is a huge French utility company which owns the nuclear reactors in UK, and Jacobs, which are users of the MoFEM. So if you are interested, please please contact us or take the picture of this QR code, which will give you a link to the web page when you can apply. Okay, so why do we really need mixed formulations for nonlinear solid mechanics problems? Because we can easily estimate the error. That is important. If you want to make a judgment about the structural integrity problems of the structures, you want to know how big errors you are making. And then when the problem is nonlinear, estimation of these errors can be costly or difficult. When you use the mixed formulation, you can estimate errors much easier. Okay, that is important because there is a risk when you make a prediction. There is a risk of the design of the structure associated with the uncertainty of the model. And then when you can estimate this uncertainty of the model by calculating errors, a posteriori errors, that is add-on. But this is a classical thing. This is what Andrei was telling to you last time. But second thing is that you can split the nonlinearities. Complex problems have a different kinds of the nonlinearities, like nonlinearities associated with the large strains, or nonlinearities associated with large rotations, or nonlinearities associated with the contact. You want to separate those nonlinearities, and maybe for some cases you want to have large strains but smaller rotations, or opposite, when you have a thin and shallow structures. Or you want to solve some nonlinear problems like related to unilateral constraint in explicit manner. By some parts, you want to solve them in implicit. So you end up with explicit, implicit formulations. So that is possible when you have a mixed formulation. It will be difficult to achieve that goal when you have a classical formulations. And finally, when you use the mixed formulation, what I will show you, you can handle greatly unilateral constraints because you're changing Dirichlet conditions to be natural, and the problems associated with the contact can be handled much easier. So we develop mixed formulations because we want to have a robustness. But as well, I will tell you that in some cases, by doing mixed formulations, and because we reduce the sparsity of the problem, we can achieve the better scalability. So we can solve much bigger problems when you use the HPC computers. And this is what emerged very often when we speak with our industrial partners, and they say that people are working as CFD, computer fluid dynamics, in the big companies have taken a big benefit from the large clusters which those companies have. But the solid mechanics people are somehow deprived from those resources because the commercial codes typically don't scale to hundreds or several hundreds of the processors. That is important if you want to design the production process, or you want to estimate the risk, and then you want to run over the different scenarios. So when you invest time in the mixed formulations, you can create the competitive advantage, which will be like attractive to industry, and more likely it will work with you. The second thing is that fidelity of the calculations, that you can control errors better, so you can precisely make a precise calculations. And then often when you do adaptivity, you can solve the problems precisely on the small computers, on the laptops. What I mean? That this picture which was showed by Andrei. So this is the transport problem. And then you can see that when I will solve the problem classically, I have this convergence rate. And then I have I start to have several millions of degrees of freedom. But then when I do HP adaptivity, I can end up with the problem which has 10,000 or 20,000 degrees of freedom. So why is that important? Now imagine that you want to provide a tool for a vast number of people, bespoke tool which solves some problem, and then you want to deploy it on the cluster. Now you can buy easily on the cloud. You can buy the cloud if you have customers. So then the size of the resources which you buy impact whether you will have a profit or not. So you not necessarily will run the problems vastly faster because it's overhead over the adaptivity, but you can run the problem at least on the smaller resources, which are cheaper to buy. Okay, so then let's give me an example how the a posteriori error estimator works in terms of the structural problems. This is a Coriolis-Lu shell, and then we have this typical problem when we have a shell with the holes. And then when we estimate the error for second order, we can see this typical concentration of the errors at the corner. So then when we make p-adaptivity, we raise the polynomial order in the places where the error is high, we start to get the uniform error distribution, okay? So this is, you can see, logarithmic scale. So then we have a uniform error. And we achieve that by raising locally polynomials orders. So then we can solve we're getting at the end, if you're doing for different mesh densities, we getting kind of the exponential convergence. Here we hit the bottom level because in that problem we are restricted by the quadrature rule which we can deploy, and then we cannot construct the quadrature rule high enough to in that case to raise the polynomials above 8. Okay, so this is about being efficient in what you are doing, but all comes with kind of the cost. Yeah, your code becoming more complex and then requires to have data structures which can handle heterogeneous approximation orders, enables you to raise the locally approximation order, and allow to do that efficiently. But ultimately, this is another example. It's not solid mechanics, but this is what we can when we run the scalability test at some point. So what you want very often, that you want to solve the bigger and bigger problems. This is the problem when you have like kind of the jet stream, and then this jet stream due to the Coriolis force, because this is a surface of the Earth, try to make these kinds of the big weather on our planet. Okay, but what I want to say, that ultimately when you construct any problem, whether it's solid mechanics or fluid mechanics, you want to construct it in such a way that you can solve it using a multi-grid solver. because this with the multi-grid solver, you can get the good scalability. But the multi-grid solver only works when you have a certain type of the matrix, and then it will not work with the subtle problems. But mixed formulations, from the other hand, create the subtle problems. So creating mixed formulation by itself is not enough. You have to make a mixed formulation with the right preconditioner that allow you to deploy at the end multi-grid solver. So this is essential. All the solution which can be applied in practice has to be a holistic. It not only has to formulate a good finite element, but as well it has to come with the package, with the solver that can solve the emerging system of equations. And if you cannot solve this emerging system of equation efficiently, then the application is in doubt whether we can apply what you are doing. So then what we're doing, we try to create the competitive advantage. So we have novel methods usually require a new data structures. The new data structures are hard to integrate with the commercial codes. So then this is the dilemma which we have currently doing as a people doing computational mechanics, because computational mechanics is applied science. So how we can make our methods applied in the industry, and then they cannot be applied through the commercial codes, because if the method is really advanced, the existing data structure in the commercial codes are not fit to the formulation which we propose. So the only way how you can progress forward is to develop research software at industrial standards, that it can be applied in the industry. Open source is the way how you can do it. But however, it's a threshold for adoption. I don't know if you hear, but I have a fire alarm at that point. It is only test. It will go away. But okay, it went off. So then software has to be designed to lower. So then we have to develop software, research software at industrial standards. But however, the open source research software is hard to be transferred to the industry. So we have to because it has a higher probability of bugs, because it's tested by smaller number of people than the commercial codes, and then don't have a human resources with the commercial codes. So we have to develop the code, design the code in such a way that lower the probability of the bugs. Okay. So at the end, because this threshold between the open source code and the commercial codes, the risk of using it, training up people, is extremely high. In order to make your methods to use the industry, you have to create the competitive advantage that your code can solve the problems with where the commercial codes fail. And that happens on the fringes when you're dealing with the really nonlinear problems like contact, fracture, or you both act simultaneously, plasticity, when you have extremely large deformations. So you have in realm of solid mechanics, you have to look at those places or impact. So what we really do, we very often try to develop the novel methods, and this is kinds of the fishing expeditions to Amazon forest or to Loch Ness. We try to we explore, and then we try to find the new way of solving our problems. And this is and then hoping that we'll have a fish which will be big enough that it will be so attractive that the industry will like to eat it. So then now I will go to more technical talk. about the multifield plasticity. So, so then we're thinking about problems like that, cold forming of the materials, that you form the material, as you can see on this picture. This is a courtesy of AFC RC. This is in Scotland, research center for manufacturing. And then, so then you can see there are large deformations that when you want to do elements like that. So then, and there is a big problem because you cannot, the calculations with using a standard computational plasticity takes a long time. And then we don't know whether those calculations are really accurate. The prediction of current codes is in doubt. So what we try to do, we try to, instead of applying explicit method, we try to apply solve that problem applying implicit time integration, because that allows us to control errors better, so we know whether we are wrong or right. We try to depart from Lagrangian formulation, what typical codes do, because when you have large deformations, what you have to do, you run the steps using a total or updation Lagrangian formulation, and then you remesh, and then you map the history variables from plasticity to new mesh. So typical formulations are Lagrangians with this mapping, which looks kind of ALE integration, but it's not truly ALE formulation. And they are based on the classical plasticity formulations, which were established by the SIMO in 70s. Great men, enormous impact. Often requires remeshing and transfer of integration points, and is computationally at the end expensive. So then what we try to do, we going into the fishing expedition where we try to solve that problem in much more efficient way. So we try to make it implicit formulation and robust, modular, and open source. So the key thing, what we try to do, we try to understand how we can do ALE formulation. So when we have a rotating body, but we don't rotate the mesh. Only material, mesh is fixed, but the material underneath is rotating. So we introduce so-called, we have a reference material, and then we have a current formulation, material formulation, which is rotating body, and then we map that to the spatial configuration. So what happens that we make a mesh over here, and because we have this rotation built in the formulation, our mesh don't have to move. Rotation happens underneath, but that requires that we depart from classical computational plasticity formulation. One quick reminder, you may not know it, we will use the Henke strains in both examples, which I will show you today. So then how you derive the Henke strain. So then you have a typical green strain, U is a stretch. So then when you take the gradient of the formation, you do a polar decomposition. So you can find out that if you apply the RU polar decomposition into the F, you can find that the left Cauchy green is just square root of stretch, okay? And this is the green strain. So, and then when you because U is a symmetric and positive defined matrix, so you can calculate the eigenvalues, which are real values over here, and then this is eigenvectors. So then the green strain in the eigen form can be expressed as you can see over here. But people are great because then they see the formula and then they say, what if I, instead of 2, I will put any number? Theoretically, you can put any number over here, and then you will get the different family of the strains. I will tell you exactly the same thing, because the strain is everything what is not rotation. So that definition of the strain will be valid for the case when you will put 1 over the 4 over here and 4 over here. So then we have these generalized strains when you could put any n, in fact, and each of those will be equivalent to any other strain, because it's everything except the rotation. So when I will when I will look at this kernel function over here in that form, it should be n over here. I apologize for that. And I will go with n to the limit. I will get the logarithm of lambda in the limit, because that function in the limit is a logarithm, natural logarithm of lambda. So I have a so-called, I define how my Henke strain look like. So I can have a general logarithmic strain, but general logarithmic strain with any base 10 can be transformed into the Henke strain with this simple formula. Okay, so Henke strain is a logarithmic strain with base e. This is how we call it. Okay, so now so then what we can do, we can calculate gradient of the formation, and then we can change it to the Henke strain. And now when we have a multiplicative plasticity, when we're using a gradient of the formation, a plastic gradient of the formation, with the trick with the Henke strain, we can change multiplicative plasticity to the additive plasticity. So now when we develop the model for the plasticity for small strains, so instead of the small strains, we'll use the Henke strains, we will transform our small strain model into the large strain model, when we will just substitute, instead of small engineering strain, a Henke strain. Okay, and then instead of the calculating Cauchy strains, we'll calculate so-called Henke strain. Okay, but there is a procedure how when you know the Henke strain, you can calculate the Piola stress, and everything works with the large deformations. So we have a balance of equations, conservation of linear momentum. We have a definition of the Henke strain, which I explained before, and then we have a definition of the Henke stress when HP is a plastic deformation. This is our stress measures, which will work. The key thing is that, because we will work with metals, we focus here on the metals, we'll assume that the trace of Henke stress is equal to 0. That is equivalent to having large stress incompressibility, because determinant in Henke stress, when you apply the exponent to it, it will become logarithm to it, it will become to the trace, become a trace. And when you apply the exponent to trace of the matrix, you will get the determinant. Mathematics is cool in that case. So then what we have a yield function, as you can see, nothing special. This is deviatoric part of the Henke stress. Typically, you will have a Cauchy stress over here. This is some hardening. Then we have a flow rule. We're using associated flow rule, which emerges from the plastic surface. And then we have a Kuhn-Tucker conditions, which distinguish between the domains in stress space, which are elastic, and the surface where you have a plastic flow. The state outside of the plastic surface is not admissible. Tau dot is Lagrangian plastic multipliers, nothing special. But what you can do, you can change these constraints, Kuhn-Tucker constraints, into this nonlinear function. So when you will work with this nonlinear function, you will find out that you will get Kuhn-Tucker conditions emerge, depending what case you will put. So, for example, when you put f smaller than 0, evaluation of this function will lead to the conclusion that Cn tau dot has to be equal to 0, which is the case because the Lagrange plastic rate of the Lagrange plastic multiplier has to be equal to 0 when you are inside of the plastic surface. However, when you will be on the plastic surface or outside of the plastic surface, those terms will cancel, and then you will get the equation f has to be equal to 0, which is as well true. Cn is here a stability parameter, which controls the convergence. It will not affect the results. This is how it's made. So in other words, when I will plot that function in this form, it looks like this one. And then when you solve the problem, you try to be on that red line. This is when you are in equilibrium. It has this non-smoothness over here, but this point is only one point of the non-smoothness. So it's equivalent to active set method. So then you don't have quadratic convergence for your Newton solver, but when you are you start to be close, you retrieve the quadratic to your equilibrium. You retrieve the quadratic convergence. But that is exactly the case when you run the plasticity in the classical way. Okay, so then this is the we have flow rule, we have a consistency equation, complementary equation. So what we can do now, we can deploy on that our beloved mixed formulation. So we will decide to have a displacement in H1, so conforming finite elements. Then Lagrange plastic multipliers in L2 space, and then Henke stress in LP, L2 tensorial space. So we'll approximate symmetric tensor on the mesh. So then we'll have for displacement, we'll have a degrees of freedom on the nodes and potentially on edges and faces, but on the nodes. But for the Lagrange plastic multiplier and Henke stress, we'll have a degrees of freedom exclusively on the interiors of our elements, faces, quads, and so on. And then, so then what we do, we write our conservation of linear momentum in the weak sense. Then we put the formula for flow rule, and then we deploy on it Galerkin method, as you can see. So we wait. So that equation has to disappear for any variation of the HP. And then we have a consistency equation when we test it by the tau, which is our plastic Lagrange multiplier. Okay, so as a result, you will get that system. No return mapping anymore. We have this sparse system, but this system has many degrees of freedom, because you can imagine in 3D, for every volume, you have 6 degrees of freedom for every base function over here. System becoming very large. So immediately you can ask the question, a question whether that approach will be efficient. Okay, Paras, you have a question. Go on.
Yeah, hi, thank you. So I did not get this point when you said, like, for the Henke strain and this Lagrange multiplier, we will only have degrees of freedom within the interior. So the question now is, if a field is H2 in the strong form, or sorry, H1 in the strong form, like the displacement field, then we know that in a standard finite element context, we do it with polynomials. And it will be C0 in a global level, and inside an element, it could be PK, whatever polynomial you choose. Now, if a field is to be L2 in the strong form, this means we would do it in the finite element sense by constants in each element.
If you will choose the first polynomial order to approximate it with the first polynomial order, that will be a constant. But when you will choose to have a first order, it will be a plane, yeah, and then some cubic function. So then you can raise the polynomial sorters, but what you don't enforce the conformity between the elements. So you allow to plastic multiplier to grow in the element and create the gap on the borders between the elements. That's why this is done by L2 space. L2 space is in the way allow you to have a jumps between the elements, jumps of the function. Okay, which makes sense because when the plastic fronts develops, you have elements which has zero plastic strain, and then next to them you have a stress element such a way that the plastic strain is not zero, so you have a jump on the border. So that's why you have to have L2 space, because if you will not choose L2 space, you will be not able to reproduce classical plasticity results. The key thing is like that everything was done Simo and all the people after him, we have to get exactly the same results which they having with the new formulation, okay? Because their results are correct. So in order to reproduce their results, that you have two methods which are equivalent but dissolved in a different technique, you have to make Lagrange plastic multiplier and the plastic strain to be approximated in L2 space.
But
That's
then, yeah, can we say this is something like a higher order or some n order DG method?
No, because we still using classical formulation for the conservation of linear moment.
No, I mean for this field, for tau, for example.
No, because we don't. So when you use DG, you have a special integration of the skeleton, which bonds the fluxes, transfer of the fluxes of the moment across the elements. Here we don't have to do that because we don't have equation which requires to do that. Okay.
So basically, then we'll have, let's say, per element separate degrees of freedom.
Yeah. So then we'll have when you will use, for example, when you will choose h to be approximated as a constant, per element, you will have a 6 degrees of freedom. But when you will choose to have a linear function in 2D, in 3D, there will be 4 times 6. 4 times 6 is how much? It's 24 preferably. So it will, you see the number of degrees of freedom will very quickly grow. And then you can see as consequence of that, that this is the displacement over here. This is the Henke stress, and this is tau. Yeah, so this is a big block. So there is many degrees of freedom over here. But what you can see that this matrix is sparse. So there is a hope, you can say, because the solver, speed of the solver, not depending not on the number of the degrees of freedom, but of the sparsity of the matrix. So this matrix is very sparse. So then when you will have a clever solver, you can be fast. At least you can scale your problem. You can solve it easily. It can scale well when you increase the number of the processors.
Okay, thank you.
Okay, so what we can do now, we can deploy. We implemented that method. We publish a paper, and then one of the tests which we run is like combined test when we run this indentation. This was done by our colleague, who is a principal developer of MoFEM, when he was a postdoc with us. Now he developed Star CCM, but he's still working for Siemens, but he's still a co-developer of the MoFEM. I'm saying that thing, but working with us, being a postdoc, will train people using a C++, and then that opens the whole set of the different careers that you can migrate to the industry, because you will have not only a skill about the computational mechanics, but you will have a skill in the programming. Okay, and then applying the multi-field plasticity, we can see we recovered results from this paper. There is a small difference because we don't have here friction, and those people states which run that test at the friction. That's why you have these elements like that. But overall, the friction is not a major first order phenomena over here. So we have a relatively good match. Okay, so then we have to tackle the problem which we have over here. And this is the same problem with Ignatius was saying on the first lecture when he was comparing the Taylor-Hood element with Cuvier-Riviat element, that you have a L2 space for pressure. So then that maybe you have a more degrees of freedom, but you can make a better solver for it. Okay, so this is the what we have this sparse system. So then we have we need efficiency to solve dense meshes at the contact zones and small time steps due to high angular velocities, and then we have a multi-field enables accurate simulation all from forming, but that can happen only when you will have appropriate block solvers. Okay, so then this is the problem which is typically you have when you will solve it with the classical finite elements. So we can employ the robust preconditioners, but we don't develop those robust preconditioners. We built it on the top on the field split preconditioner, which was developed by in PETSI by Jed Brown. PETSI is a great tool. It's fundamental to everything what we are doing. Okay, so how you tackle those problems? If you want to solve the large systems, you want to solve them in using iterative Klirov solvers, but the iterative Klirov solvers works well when you apply the preconditioners, and then you can have two types of the preconditioners, left and right. And then we will here assume that only we will be using left preconditioner. And what preconditioner try to do is try to make our matrix K as diagonal as it can be. Okay. So it's try to diagonalize the matrix. So then convergence of the iterative solver is fast. So you can see that in order to have a holistic solution for a mixed formulations, ultimately you have to think about the solvers. Okay, but there is a way you can so-called calculate the Schur complement. This is explained by when you Schur complement is a way of the Gauss elimination on the blocks. So what it does when you multiply matrices in a certain way, you diagonalize your matrix. So when you have a diagonalize the matrix, you can solve first for example, for plastic strains because it's diagonal as a one block, but this is cheap to solve because it's diagonal. And once you have that, you solve for rest of the block. Okay. So in other words, by doing that, by applying the Schur complement in the efficient way, you're removing the block from the middle, and you end up with a smaller problem like this one. And then here is tau and u. P, EP disappeared. Everything's shrinking. And then when you apply the Schur complement again, you end up with the matrix, which looks exactly the same like it will look in the classical plasticity. Okay. And then on that matrix, you can deploy GMRS solver and solve that efficiently. This is the very old results which we have, and then we don't have a good implementation, but I can show you how it look like. So then this is a runtime with the different solvers, how we, on the different levels for the different partitioning. But what we were looking up at that point, whether even if we have like not the best implementation at that time, whether we'll have a scalability. And then we'll find out that by applying the Schur complement in this systematic way, because we're exploiting the L2 spaces for our Lagrange multipliers and HP, whether we can scale our problem. And we could, as you can see, the scalability looks pretty nice. But when we look at the problems, but there at some points we reach the limit, and then you can see this deterioration. But this was a matter of the better implementation which we could apply. Wait a second. So this is a necking problem which we will solve during the tutorial. Similar problem to that one you will solve with the tutorials. Okay. So, but what we have found that, for example, when we will use the MOOBs, we will direct solver will very quickly reach the limit, and then solutions will get slower. Yeah, but when you use, for example, multigrid, algebraic multigrid on the Schur complement, or block Jacobi on the Schur complement, we can get the much better speed up. These results for the multigrid are not necessarily the best which we could get, because we don't exploit the local block structure of this U matrix matrix. But what I want to say, that when you will compare the time against the number of degrees of freedom for formulations like that, taking in factor that this is not the optimal implementation, you can see that despite the number of degrees of freedom, the times are not different. But what you can see, this is what you are looking for, that when you take the classical formulation for a plasticity and multifield plasticity, at some point, those two lines will cross. So when you will start to solve bigger and bigger problems, which are industrial problems, there you will have a moment that the going in the formulations like this one will be more competitive. And then on top of that, when you will improve your implementation, you can shift this point when those two lines are crossing for smaller and smaller number of the degrees of freedom or elements. Okay, we describe that all this thing in this paper. You can look at that thing. Okay, I think that I will stop over here and then take questions if you have for me.
Yeah, we're good to go now.
One important comment. So then I presented to you exactly the same version which you find in the paper which we write with the Carol, Ignatius, and Andrew recently, and published in CMAME. But version of the code which you will be running is an improved version of the published code. So when you will run those tests, you may see if you will have run them on the bigger machines, you may see that the results will look a bit better. And then moreover, the formulation which you will have in the notebooks allows you to run both hex and tet meshes. You are free to choose the mesh, and then allow you to run 2D and 3D problems. The same code run 2D, 3D, hex, tet, quad, and triangle meshes. In 2D, you can mix the triangles. You can make a heterogeneous meshes, mix the elements, triangles with quads. In 3D, it's not working because we don't yet implement the wedge element into the code. And then sometimes when you make a meshes, heterogeneous meshes, which mix hexes and quads, tetrahedrons and hexes, you have a wedge. You have to put the wedge, and then that is not working. But key thing is that you can raise the approximation order, and then you can approximate geometry in the arbitrary way. If you are interested, please tell us, because tomorrow at the end, when we have a spare time, we can show you a structure of the code itself, how those operators which calculate the different bits are implemented, how the Schur complement is calculated, and so on. We can show you, point you to the source code where you will find how the things are done. But what is the fusing element of the plasticity and mixed formulation for large strains is a contact. So then I will tell you quickly about the contact. So some time ago, when Andrei came from us, Andrei was working on the problems of the contact and the lubricating of the surfaces when you trap the fluid on the rough surface, as you can see on the figure. But most importantly, when we start to work on the another problems, we find out that the high calculations of the contact area with the contact with the surfaces is essential. So then we start to look at the problem that you have a rough surface, as you can see. Maybe you can even take the truly rough surface from the experimental data, and then we press the rigid flat into it, and then like, for example, you have soft material, and then you put the glass into it, and then you see how the contact area develops. So then in that case, we want to calculate, Andrei want to calculate precisely the contact area. So then the problem looks like that we have stresses, conservation of linear momentum, in that case, not body force. We don't apply body force because this is a small thing, so the inertia body forces can be neglected. Quasi-static problem. And then again, like in the plasticity, we have a unilateral constraints because we have these two regions of the elastic domain and the plastic surface, and then switching between them. Here we have a contact and no contact. Again, unilateral constraints. Okay. And this is a headache, because when you have something non-smooth like that, inequalities, it means that there will be a Newton will have a problem with that. So of course that then you can discretize everything, and then you can express these unilateral constraints with the C function, which will appear somewhere here. Okay, you can as well add some regularization, which will help the Newton to converge. And typically you can, so then you will have, so then contact is a Lagrange, is a constraint, so it has a Lagrange multiplier with it. So we have a Lagrange multiplier, which was a plastic strain, Lagrange plastic multiplier, and here Lagrange multiplier has a different interpretation, has an interpretation of the traction on the surface. So, but because this is some field, so you can ask is valid question, what is the space we should choose to approximate the field of the tractions Lagrange multipliers on the boundary? Wrong choice will lead to the instabilities, propagation, pollution of the solution by the errors. And then you will see spurious oscillations, for example. Okay, so typical choice could be that to choose the approximate the tractions in H1 space. So then when we reduce our case to this problem, for example, test 2D, we have a wavy surface, we have a rigid flat, and then we press a rigid flat onto that surface, and we can study what will happen. And then what happens when I choose the H1? We choose the H1. What happens that when we have analytical solution in red, and finite element solution, we cannot avoid to create the error on the front of the contact front, because there will be a case that the contact front will be not be precisely on top of the node when you can have a kink, but it will happen inside of the element, in the interior of the element. Contact front can be in the interior of the element, and then there is no way you will make a numerical error over there. That is okay, yeah, because this numerical error will go smaller and smaller when you refine the mesh. But you have to check what this error will have, effect on the elements nearby. And then when you have stable solution, because the disinvariant principle, this error will be contained. It will not pollute the rest of the mesh. If your approximation is unstable, this error without the resistance will propagate into the mesh. And then what you can see over here, this error propagate into the mesh. Okay, so then when you will zoom, you can see it over here. Okay. On top of that, you have error propagate. You may not see it, but it's error propagate into that direction. But now everything is wrong, because this is contact, this is no, so that this is no contact, this is contact. So the contact appear somewhere here when it shouldn't appear. Some kind of the oscillations which Andrei showed you with the thermal problem, that's wrong. Okay, error which happens over here propagates and pollutes the solution. That means that it's unstable. Of course, those oscillations depends on the stabilization parameter in some way, and then the stabilization is problem of the robustness, and then how to choose epsilon. For what epsilon this stabilization parameter, our results are good in C function. Okay. So, but then when you open books about the mathematical foundations of the finite elements, you will find out that the displacements inside of the volume are approximated in H1 space, but the trace of the displacements on the boundary, trace of those displacements on the boundary, so how those displacements emerge on the boundary, are in H1, this fractional space, 1/2 space. Okay. But then, but everything has to be dual. So then this gradient of the displacements works with stresses. Displaced trace of stresses on the boundary works with the tractions, create the work. Those things are dual. So the dual space for fractional space is 1 minus half space. Okay, so the natural thing to approximate the Lagrange multipliers will be not, in fact, to use the H1 space, how it's done classically, but to approximate it as a trace of the H-diff space on the boundary. And then we can hope for a solution. So again, we're using the similar concepts which Andrei was presenting to you, talking about the mixed formulation. Okay. So let's try see what will happen in that case. In that case, when you will look at this, we will find out that those oscillations which we have disappear. Okay, we get, this is red curve. We have an error over here, but this error don't propagate into the mesh. It's contained over here. This is the error. The solution should be like that, but we are over here. There is no other option. Yeah, And then solution. So then you see this corner when we cut the corner over here because our contact front is in the middle. Fine. We have when you will refine the mesh, that error will disappear. This area integrated of the difference between the dotted black line and the blue line will be getting smaller. But our error is not polluting rest of the solution. This is the key. That solution is stable. So the mixed elements save us, and then and the problem, and you will find the set of the problems that this is fundamental. Okay, so then our Lagrange multipliers we're making in that case we can construct the variational problem, and initially everything is similar to the classical formulation we're using a different space. But the key thing is that, which we unfortunately have not time to discuss that in depth, that how to calculate then properly norms for those fractional spaces. And it's coming that those norms of those associated with those fractional spaces can be calculated in volume. So then extension of T. So then what we really want to have, we want to approximate the tractions. We want to approximate Lagrange multipliers in the volume. And then we want to take the trace of those Lagrange multipliers. The trace of the Lagrange multipliers will appear as a traction in the boundary. Okay. So the tractions are our Lagrange multipliers times the normal vector, when phi, j, m are the base functions for the H-diff space, exactly the same base functions which Andrei was using in the first talk. Only one important information, that in order to everything work, you have to have one-to-one mapping between the tractions and the approximation of the Lagrange multipliers in the volume. I will show you in the second how it looks like. And then just if you will look at the mixed form H-diff space, the H-diff space works like that some trace of some functions in H-diff space is 0 on the boundary. So the mapping, this mapping from the H-diff space to the boundary is not unique. But but when you restrict your H-bit space to the Thomas element, you will have one-to-one mapping. So this is all the H-diff base functions restricted to RT space. Then in that case, we have one-to-one mapping, because RT space guarantee that the trace on the boundary is not 0. And then you can prove when you can see the proof of that when you look into the Buffy book, this yellow book about the finite elements. And then you will find out that when this condition appears, so the trace, so when the approximation of the Lagrange multipliers times normal to the boundary for any test function in the H half space is equal to 0, only if that is equal to 0 only when lambda is equal to 0. So then you will have a Riviat-Thomas space, and there will be one-to-one mapping, and as a result of that, we have this injection. So then in our formulation, we will approximate the Lagrange multipliers in RT space. I lost one slide. Okay. Oh, no, I have it. So now to capture the Kuhn-Tucker conditions for Lagrange multipliers for contact and non-contact, again, we're using this complementary function, which is written in that form, which works similarly to the function which I presented, was presented to you for the plasticity. So when you will have a contact, all the terms disappear, only TC will appear over here. And then that function will yield that TC has to be equal to 0. So traction has to be disappear when you have not contacts. But when you will have interpenetration, that function will cancel all the terms with TC, and the gap function will only appear. So it will tell that the gap has to be equal to 0. So you penalize the interpenetration. And this is how it will work. So everything over here works a little bit different than in the classical formulation. So first, we integrate things in the volume to calculate properly norms of the Lagrange multipliers. And then we have terms with the constraint functions which are on the boundary. And those two terms are and then when the contact happens, so some terms C functions switch off functions which are associated with the boundary integral, and then it's prevent the penetration. From other hand, when you have no contact, the boundary integral and volume integral cancel each other, and then you allow ourselves for separation of the bodies, so then the positive gap. So all those terms can be represented in this form. Unfortunately, with the time limit, I don't have a time to explain all the details here, but I will a little bit explain you how those boundary and then and volume integrals are calculated in the next step. The problem is over here that the things are a little bit upside down over here, because when I add the Lagrange when the Lagrange multipliers, because I constrain the problem and then I release it, is opposite that is happening the classical problem, the contact problem. That in the classical contact problem, when you add the equations, you constrain, and here when I add the equations, I release. It's similar story which Andrei tried to convey when it's showing a difference, that Dirichlet boundary conditions becoming natural and natural boundary conditions becoming Newman boundary conditions becoming essential. Nevertheless, I will show you how that look like. So then this is you can see inside of those triangles approximation of the Lagrange multipliers in HD space. And the trace of those Lagrange multipliers generate the traction. Okay, so then when I have this cylinder which is pushing against the rigid plane, I have a contact, those Lagrange multipliers generate the traction. But when I calculate the sum of the integrals in our formulation, because it's HD space, I can calculate in the volume. And and only integrals which are associated with the Kuhn-Tucker constraints, with complementary functions, are calculated on the boundary. That gives us a stability and remove the oscillation. And then you can solve then more complex problems immediately. And then everything works with you can see hex meshes in the stable manner, and then you can have a large curvature of those elements. Okay, and then we don't have a propagation of the error inside of the volume despite the mesh is very close. So the geometry here is approximated by the third order polynomials. Or you can solve the contact problems like this. Everything can be validated, of course, against the Hertz problem, and then again, which shows that those errors stay contained; they are not propagated in the volume. But now I have to go. I will try to show you more about this HD space, which will don't bring the full clarity about the contact formulation, but it will shed some light on it. But before that, I will have to go back to the situation when we have a reference configuration, large deformation, we have a current formulation, and then I will introduce the intermediate configuration. So we will have a mapping from reference configuration on the form body to the to the, wait a second, I have to make a move. We have this intermediate configuration, and then when we move from the intermediate configuration, we have a current configuration, and this current configuration is in equilibrium. So we can, so then moving from here to there is a composition going from here to there and from here to there. So then we have this to the intermediate to the intermediate, and from the intermediate to the current. Okay. So there is another thing which I want to introduce is a definition of the. So then we have to. I will try to approximate the rotation. So I will introduce the definition of the. I will approximate the axis of the rotation. This is the vector, which represent the. So then I approximate the axis of the rotation. Okay, so this is the omega, and then the length of that omega is angle of the of my rotation. Okay, so then when I take the so then I can when I can normalize it, this is unit vector. So then when I multiply the unit vector by Levi-City tensor, I get the skew symmetric tensor, which is A. And then when I will use the skew symmetric tensor and then apply the exponential map to it, I can get at the end the thing which is called Rodriguez formula, that I can represent the orthonormal vector, rotation vector, by omega. And this is exact formula. So if I have omega, I can change the omega into the rotation. So what I can, so this is gives me idea that I can approximate the rotations directly on the mesh. Okay, by approximation omega on the mesh when the omega is a vector. Okay, so that will be essential to understand what happens with the R and this decomposition in the second. So then what I can do, I can write the formula which looks like this. Okay, so this is I can find out that F, okay, gradient of deformation is du over dx plus 1. Yeah? And this is equal to d small x dx. So when I will use that, and then that F is equal to R times U, when I use those two things, I can get this equation, and then I can test that equation by P. And the P is here a Piola-Kirchhoff second tensor. Okay, so then I get the equation, so which I will call the consistency. So then I use the polar decomposition. Okay, and then I finding the consistency between the approximation of the rotation, stretch, and the displacements, and I test everything by the Piola stress. That equation is very similar to the consistency equation with Andrei had for thermal problem. It's practically the same, only with this one difference that we're working here with the tensor, not with the vectors. Our flux is a tensor, not a vector, because the stress is a momentum flux. Okay, in that case, so then it's represent flux of the momentum through some arbitrary surface. So we have a Piola stress over. So when I have this formula, this is, I call it consistency equation, I can calculate the differentiation by parts of this equation, and then look what happens. This gradient disappears from my equation. So as a result of this, I don't require that my displacement will be in L2 space. But another thing appears, that the boundary condition on some part of the boundary, when I have a constraints, start to be added to my equation. So that's why I will call it that is natural boundary condition. Okay, you see that in this case, the kinematic constraints, Dirichlet constraints becoming natural, like in Andrei problem. In Andrei problem, constraints on the temperature becoming a natural constraints. That is super convenient because when I deal with the contact, yeah, and then that's why I will have a part of the integration in the boundary, and so then here when I will refer to the contact, here instead of that U, I can put the complementary function, C function, okay? And I can manage contact in that case. Okay. So I apply, so that movement from this equation to that equation is differentiation by parts of this term. As a result, the natural boundary condition appears. Okay. So this consistency equation I write over here, but in order to everything to works, I have to add more equations to solve my problem. So I have to add the equation that my approximated Piola stress is equal to the Piola stress, which I calculate using stretch. Okay, because I have over stretch, so I can calculate the Piola stress. And then so I have a Piola stress which coming from my constitutive equation, whether it's Neo-Hookan, Kirchhoff de Sanvenant, Henke constitutive equation, whatever it is, I can calculate it using the stretches. And then, but from the other hand, I want to approximate the P, Piola-Kirchhoff, momentum flux, like heat flux, and here I have a momentum flux, and those two things has to be equal to each other. Okay, so this is so then this equation I will call the physical equation, consistency equation, physical equation. But on top of that, when I will push my Piola-Kirchhoff to the current configuration, I will require that my Cauchy stress is symmetric. Because when the Cauchy stress is symmetric, it means that I conserve angular momentum. So I approximate the P, Piola-Kirchhoff stress, momentum of flux in H-deep space, but my space itself a priori don't enforce the symmetry of the stress. So I have to add the additional equation which enforce the symmetry of the Cauchy stress or enforce the symmetry of second Piola-Kirchhoff stress. And this equation enforces that thing and is tested by angle of the rotation, variance of the angle of the rotation. Okay. And then I have to add additional equation, which is a conservation of linear momentum. So you can see in this mixed formulation, I see all 5 equations of the continuum mechanics as a separate equations, where I enforce the conservation of angular momentum in the weak sense. There are formulations for small strains which build the tensorial H-diff space such that they guarantee symmetry of the Cauchy stress a priori. However, they are not necessarily give you any advantage, and that formulation gives us some more flexibility. But there we can apply even deploy one additional tweak, unusual trick to what we are doing. And this is what will happen here. Because in order that to work, we have to have approximation of R rotation, stretch. So that will compose as F, but then we can now, because we will approximate the stretch, how we approximating plastic strains, we can choose what we approximate. So for example, we can, instead of approximating a stretch directly, we can approximate the logarithm of the stretch. So then when we will take the exponent from the logarithm, we'll get the stretch itself. Why is that important? Because stretches can be only positive numbers. You cannot have a negative stretch because it will mean that you will invert the material. Stretch cannot be 0 because it will mean that you can compress material to such a point that it have a 0 volume. That is not physical. So there is some barrier in every physically proper, accurate physical constitutive equation that prevent to stretch to becoming a 0. That is typically realized by some logarithmic barrier function. For example, Kirchhoff-de Sandvenant material is not the proper constitutive material because it will not prevent the interpenetration. Okay, so in other words, in our formulation, to be to increase the robustness, now we don't have to approximate stretches. We can approximate Henke strain, which is the logarithm of the stretch. So doing that, last thing, we can take the physical equation and then we can reformulate this physical equation to operate purely with the logarithm of the stretches, and everything will work. Looks complex, so you have to have a software which can handle such complex things in the easy way that you can easily implement those things. If you will have questions about that, we can show you a code. In fact, you can dig out this code by yourself in your notebooks if you like. Okay, but one thing, cherry on the top, which explain the reason why we introduce this intermediate configuration. There is a old theorem proven by Stenberg in '88 in Finland, and it shows that for small, everything was done so far for small strains. What we try to do novel over here, we try to do everything for the large strains and have additional benefits from the mixed formulation. And he proved that for small strains, when you project the displacements U, which now can be approximated in L2 space, to the H1 space, you solve your problem and then you do a projection from L2 to H1, you automatically get error estimator of your solution. So then you have estimation of error for free, which can work in the nonlinear large elasticity case, which is a big problem. But now, because we're using mixed formulation, that problem disappears. So what you can do when you solve your problem using mixed configuration, you have this shadow intermediate configuration which follows you from one step to the another or from one iteration to the another, and then project constantly the displacements as a post-processing from L2 into the H1 space. It's improving your solution because you can see the norm, the K plus 1 is jumping up. So then error drops because by projection itself. And then on top of that, it's give you estimation of the error, which can drive your mesh adaptivity when your structure undergo large deformations. We don't explore that yet, but we're thinking that imagine that when you have a large problem and then, for example, skin, and then you try to compress it, the wrinkles appear. So then when the wrinkles appear, you will have suddenly need for much bigger resolution for denser mesh locally. So you will drive that refinement for large strains by this proper error estimator with strong mathematical foundations. I will say only one thing, that the necessary condition for ideal robustness is that the energy of the discrete system remains finite regardless of any random value of degrees of freedom. So imagine that if you have a classical formulation, and then you will randomly choose the values of the degrees of freedom, like you will use the random number generator to put the numbers for values of the degrees of freedom. And then you will calculate the energy of this random state of the system. When you have a large strength, very likely you will get the infinite negative energy or infinite energy, which is impossible. So it means that, but from another hand, when you solve the Newton problem, you can end up on the another side, on the negative side of the stretches. So when you approximate the stretches, you can end up with because the Newton method is try to converge, and sometimes it will go off tangent, and then it will go into the to the zone when you have interpenetration. It will generate the negative stretch. Your constitutive equation will blow up, and then you will have to restart the calculations from the smaller step. That is a big bottleneck when you have calculating, for example, impact. So then you have a soft body which impact the wall, and then in the moment when you do a large step, and then when you enforce the constraints from the impact, from the contact, then you're generating inverted elements. Your situation, your system blows up. You have to reduce the step and try again, reduce the step again, and then at the end you end up that when you want to have a high velocity impacts for large strains, the only way is to doing explicit method, because anyway you're making a small time steps because you're constantly generating inverted elements, your energy blow up. But here we approximate the H logarithm. So then that situation not necessarily will appear. Yeah. So then this is you can see that I'm talking about the problems that you have a really large deformations, and then you don't want to have in any case your simulation blow up. Okay, just to sum up. We approximate, you have a mixed formula, mixed element, which approximate the pure Kirchhoff stress in H-diff space. That space has to be, which has zero trace on the boundary, is lifted by the applying essential boundary conditions to the tractions, exactly the same what happens with the Andre formulations, that the constraints on the fluxes were essential. Then we approximate displacements or logarithm of the displacement, rotations in L2 space, or when we and then Henke strains in L2 space as well. One thing more, so then this space for a pure Kirchhoff will restrict ourselves to the Riviat-Thomas space, but to it we will add a special bubble function which guarantee stability of the formulation. And then if you, we don't have time to dive into it, but you can look at the second elasticity element using the bubble written by Gala-Parakrishnan and Guzman, a very good paper where they proposed this function. I plotted, we implemented that function. If you are interested, we can show you where. And then this function is so-called zero normal function. So if you will look at this tetrahedron, and then you can imagine these bubble functions represent all possible ways how the incompressible fluid water can flow inside of the triangle without the leaking from it. It's zero normal because it means that divergence of this function at any point is equal to 0, and function times normal gives always a 0 traction. It's zero normal function. Okay, so the key point which Adriana will stress will be about one key element of Adriana's tutorial will be that Adriana will show you how to calculate that error when you make this projection, and then you can see how it looks like. But it's like this element has a potential. You can do a lot of things with it. Okay, so then very quickly I will point out why this element is useful. So when you there is two very cool papers by Bonnet, Antonio Gil, and then Vriggers. When those papers try to tackle the problems of the nearly incompressible soft materials, and the Cook beam is solved with it. And then the problem is that there is a large penalty on the change of the volume. Yeah, so then we don't have truly incompressible materials. That such materials does not exist. We have a nearly incompressible materials. So then, but then when you solve those problems, we have this. When you plot the gradient of deformation, the solution may look like that. I will show you only how this look like for formulation, which you will be testing by yourself during the hands-on session. That when we plot the gradient determinant of the gradient deformation, this looks nice smoothly, as you can see. And then here, just out of the interest, because we enforce the symmetry of the second of the Cauchy stress, which is calculated from approximated Piola stress. In the weak sense, you can plot the error associated with enforcement of the angular momentum. And this error, you can see, is large on the corners, and it's large over here because the solution over here is not exact, because when you will find out that you're creating the singularity over here, so you will have to have a crazy dense mesh in order to make this error go down. This is a problem, typical problem with the singularity. But added benefit is, since we approximate the stretches or logarithm of stretches, we can easily plot them when we make a formulation, because we can plot the field. Last thing, which you always have to remember when you're dealing with the mixed formulations, you have the formulation is not enough. It has to be a full package. So you can easily calculate the errors, that's fine. But if you cannot solve your system of equations efficiently, people will not switch to your method, because they will have to wait too long for the results. You can say to them that, okay, for small problems on the one processor, mixed formulation takes you slightly, it's not as fast per degree of freedom as the standard FEM, but we have benefits. But then you can say to them, but if you use my method or mixed method in the large number of the computers, my method will scale better than the classical method. And then the same story. Look, this is the approximation of the stretches over here. And here we have approximation of the, as well, we have approximation of the displacements, which are in L2. And then we have approximation of the rotations in L2. So we have maybe a big matrix, because for classical FEM, not exactly, you will have only that bit, but here you have a Piola stress, bubbles, you have a stretches, you have rotations, and then you have a displacement. But this matrix is mostly sparse and block diagonal. So you can eliminate this bit of the matrix and end up with that one. And then again, you're applying the Schur complement, and the Schur complement is in fact the one way of the multiplying your system by matrices, sparse matrices, but because those fields are in L2, you can do it on element by element level when you're calculating this inverse, this one and that one, on element using, for example, LAPACK, so and very small matrices, so you can do it very fast. And since you're doing that like in the plasticity, element by element, you don't have, you can parallelize that easily. So your problem can scale, and then you can solve big problems. Okay, so what is happening, you can eliminate the logarithm, eliminate the bubbles, because the bubbles then eliminate the rotations, and you end up with the kernel over here, which is very sparse. And on that kernel, you can deploy the multi-grid solver, and then you have optimal complexity at that point. And this matrix, in some cases, is when you have elasticity is positive, the symmetric matrix, so you can solve it efficiently. So you recover at the end. So the block solver is an essential component of the whole infrastructure. Just a last comment at the end. So then when we have a classical formulation, we have a primary field, which is displacement or temperature in H1, and then I will have a node. That node can be connected to many other nodes through the elements. So the connectivity of that node is not bounded, because it's depending on the number of the adjacent elements. Okay. From another hand, when I have my final field approximated in HD space, in 2D, I can have only 3 neighbors through the faces, or in 3D, I can have, for tetrahedron, I can have only 4 neighbors or through the faces. So my matrix, structure of my matrix can a priori fix number of non-zero elements per row. So if I want to push my efficiency of my system to the very end, I can harvest that property, because a priori, I know how much memory I know without the looking into the agency of my mesh. I have to look only how many elements I have. Here, I will have to construct the structure of that matrix. I will have to, how many non-zero elements, I have to go over every node and check what is the agency. That can be costly thing. But on top of that, what you can do, because this matrix has a fixed band, you can try to think how you can construct the effective multi-grid solvers for that. It will be much easier in this generic case. I want to say only that when you change the spaces from H1 to HD, you increase the sparsity of the matrix, you change the agency, which can be harvested in the many different ways in the future. We don't do that, but we invest in those methods because we can see a potential in them. And then very often is a potential important, that when you have the right conditions, you can exploit that potential. And potential of the mixed elements in solid mechanics seems to be a huge thing. So thank you. I hope that I am mostly on time.
Right. Thanks, Lucas, for a very interesting talk, very informative. One question from Abbas, your slide 67. So what does PC field stand for? I think that's related to PET-C.
This is 67.
Slide, yeah.
Okay, that PC field split. Okay, this is field split should be called. Okay, this is the name of the implementation of the block solver, generic block solver in PET-C. PET-C is a library developed by Aragon Laboratory, and then and field split is a nice thing because it's allow you. It's provide you with the ready solutions, but allow you to be hacked, and then you can. It's allow you to implement your own Schur complement, and this is exactly what we are doing here. We have a whole infrastructure made by PET-C, and then in MoFEM we calculating a Schur complement, and then PET-C exploit that Schur complement, and then on that Schur complement through the PET-C we can deploy algebraic multigrid, for example, or big Jacobi block solver. So then we can get the scalability from that.